All right, so this is working, and this is working too. I mean these equations. You remember that we had previously calculated horizontal stresses as a function of Young modulus and Poisson ratio and tectonic strains, which are over here, for an isotropic medium. And then we extended this for an anisotropic medium. But there was something that we were missing from there, and that was the fact that we have coefficients here, that there was a horizontal Biot coefficient and a vertical Biot coefficient. Now that we know what a Biot coefficient is, we can extend the theory of poromechanics for anisotropic media. And I'm not going to go in details of that, but I'm just going to give you the result of that. If you use a transverse isotropic medium, this is how the Biot coefficients are going to look like. The horizontal, the vertical, and also the pore modulus. Notice that you remember for a bulk porous solid, this one was 1 minus K bulk of the entire porous medium divided Ks. Well, now you have these stiffness parameters, coefficient C11, C12, C13 divided by 3. So it's an average of the first row of the stiffness matrix. And this is for the horizontal. And for the vertical, we have something similar, but instead of having C11, which is the horizontal one, we have C33 and C13. And it's also a sort of an average of the third row divided the modulus of the matrix. So the Biot coefficients are very similar, but now for an anisotropic medium, it's going to depend on the stiffness of the solid and in different directions of the porous solid. So, yes, Stefan. Ks, yeah, is the K of the skeleton. How do we call it? Ks or Km? I don't remember. Let me check. I think I call it Ks. Yeah, Ks. So Ks is a K of the solid part or the solid skeleton. So let me find. So if you compare it to this equation right here, it is very similar, but it includes the anisotropic part. So question, which one is going to be smaller, alpha H or alpha V? Which one is larger, C11 or C33? C11. And also C12 and C13, they're going to be comparatively larger. I don't remember C12 is larger than C13, but definitely C11 is larger than C33. And when you compare this, then this is bigger than that one, so it's going to subtract more, and alpha H is going to be smaller than alpha V. If you check that paper that we discussed about this model of stresses as a function of anisotropic parameters and anisotropic Biot coefficient, you will see that alpha H was smaller than alpha V. And that's because the rock is stiffer in horizontal direction than in vertical direction. And because the rock is stiffer, that means that the Biot coefficient is going to be smaller in horizontal direction. So now that we know all the anisotropic properties, you can solve for this equation. You have everything. You have horizontal Young modulus, horizontal Poisson ratio, horizontal Biot coefficient, vertical Young modulus, vertical Poisson ratio, and the tectonic strains. You have everything we need. And the derivation of these equations, again, it's very similar to this one, but now assuming that effective stress comes from the bioeffective stress, and it is exactly what we wrote this problem, which is this one, but now you have to consider here an anisotropic matrix, an anisotropic biocoefficient. You work with equations, and after 3 pages of derivations, you get to those equations. So if you don't believe me, you can try, and you will see that you'll get to that solution. And as a result, some of these stress paths and some of these parameters also, they are going to be anisotropic. So they are going to vary a little bit from what we have in the isotropic version. One more thing to add over here is that these equations that I just showed, let me find them again, are assuming, and this is going to be the connection with the next thing we're going to see, is this assuming a drained or an undrained problem? A drained problem. This is a drained problem. This is assuming that pressure is in equilibrium with stresses and strains. There is no build-up of pressure because there is no transient build-up of pressure because of stress or strain. And because this assumption assumes that in some problems, particularly those related to overpressure, whenever the pressure is not hydrostatic, you may not apply this directly because the problem may be undrained, not drained. And these are drained equations. They are drained. They are drained, yes. Otherwise, we'll have an additional term, which is we're going to see now. Okay, so with this, we finish the drained part of poroelasticity, and now we're going to talk about undrained loading. Undrained loading means that no fluid comes in or out the pore space. Therefore, let's imagine a porous solid filled with a fluid with a given bulk volume VB. What is the amount of fluid in mass inside this porous fluid, this porous solid? So if I want you to give me mass, then the mass of fluid inside this porous solid is going to be the volume of the pores times the density of the fluid. Volumes times density will give you mass, right? Okay, let's add one more thing. We're going to divide this by the bulk volume, and what we're going to get here is the mass of fluid per unit of volume. The mass of fluid in the pore space per unit of volume, because it's divided by bulk volume. So if you have a rock of 1 meter square and then you have a porosity of 10%, then probably you're going to have 100 liters of water, 100 kilograms of water. So this is 100 kilograms per meter cube, something like that. It's mass per unit of volume. And what is this? Pore volume divided bulk volume, it's porosity, right? So this is what we're going to do then. We're going to work with this equation in which we want to understand what is going to be the variation of mass of fluid per unit of pore volume by either varying the porosity inside the porous solid or by varying its density. Here we don't make this assumption of incompressible fluid flow anymore. Now we have a compressible fluid, we have a compressible porous solid. All right. just because of math, this differential can be divided in two parts, right? I can consider the first part, which is a variable, and the, well, let's do it in order. And let me find the eraser. Oh no, I think it's going to be more physically meaningful like this. All right, so one of them I consider constant, and I consider variations of the other variable, and I add up to variations to one of the variables constant and variations in the other variable, and this is the result. This is just math, okay? This is just a differential, or the rule of derivatives. Okay, now is where we start with some physics. First of all, let's take this equation and let's divide it by the density of the fluid. So here we're just going to have variation of porosity, and here we're going to have porosity divided variation of density of the fluid divided density of the fluid. First of all, if you remember, we had an equation for variation of porosity. That was the third equation of poromechanics that tells you that variation of porosity is equal to Biot coefficient times volumetric strain plus pressure divided the pore modulus. So we're just going to write this over here, and we'll write in differential form. We know the Biot coefficient doesn't change, so this one is not going to change. There might be a change in volumetric strain. And we also know that the parameter n is constant, it's not going to change. And the one that could change is pressure. So we'll write those as differentials over here. Let's see the other part. Do you remember any kind of physical law that explains variations of density with respect to initial density? What property of a fluid tells you the variation of density with respect to initial density? I'll help you a little bit. Very well, compressibility. The variation of density of a fluid because of a variation of pressure normalized by the initial density of the fluid is what we call compressibility of the fluid. So from here, I can use the definition of compressibility, and what I'm going to do is, instead of this, I'm going to use the opposite. I'm going to use the bulk modulus of the fluid, which is just the inverse of compressibility. So if I do that, then notice that this thing is what I have over here. So what I'm going to get in this equation is just dP divided the bulk modulus of the fluid. And this comes from the definition of compressibility. All right. So I think we're ready here to, yeah, we can put these two together. Oh, there is one more thing I have to do. All right, let me finish these equations. I just want to group the dP together. And dP is going to be together over here. And this is going to be 1 over n plus porosity divided the bulk modulus of the fluid, and I want this to be a constant. But do you think it's a constant? We know that n is a constant. We know that we're going to assume the compressibility of the fluid is a constant, but porosity is not a constant, right? Porosity varies. But this is where it comes another assumption in order to work these equations. We're going to assume that these are small strains, and when we have small strains, that means that the variation of porosity is small, and I can, instead of using the porosity at time t, I can replace this as the porosity at time 0. It's an approximation. It's not perfect, but it works. And with doing this, now this one is a constant. It's not a variable anymore. And this constant, it's an important constant, and which is equal to 1 over m, and we're going to call it m star. This is not the m from 1D uniaxial strain. This is another m, which is called the Biot Modulus. And it is equal to what it is right over here. And just as a reminder, let me write it entirely so we have everything in there. This one is a Biot modulus. And because this is a Biot modulus, then this is going to be 1 over n. But if you remember n, 1 over n was Biot coefficient minus initial porosity divided Ks, and this is plus porosity divided K of the fluid. So this important modulus, the Biot modulus, it tells you the compressibility of the porous solid, taking into account the compressibility of the solid, but also the compressibility of the fluid. And notice that in this summation, this term is sort of weighed by the porosity. And this one is weighed by the almost 1 minus porosity, but rigorously it should be the Biot coefficient minus porosity. But if you imagine that this Biot coefficient is close to 1, this is 1 minus porosity divided Ks, porosity divided Kf. And this is going to be a constant. Okay, for undrained loading, then this is going to be very important. And for undrained loading, this has to be equal to 0 if undrained. That means that there is no variation of any fluid mass inside the porous solid. It can compress, the density can change, but there has been no fluid, no molecule of fluid going in or out of the porous solid. All right, so what we're going to do now is we're going to use this Biot modulus in order to expand the diffusivity equation. So basically, this is conservation of mass, because this is what we have done. Mass, the variation of mass equal to 0, so this is just conservation of mass. So we can add to this equation the continuity equation, and this continuity equation, it tells me that the variation of mass in a porous solid as a function of time, it might be different than 0, but we are considering that there is flow, and the part of flow comes here. That this equation, the divergence of the flow rate in terms of mass, when you add those two together, this one has to be equal to 0. So this one is at the given point, variation of time. This one is the variation of fluid coming in different directions. So this is a gradient of rates in space. Basically, let me do schematic here. Let me go over here. If we have a porous solid, the first term is what we just did. The second term would be that, let's say, if I get 0.05 and 0.05 from here, I'm entering a total of 1 into the porous volume. Well, if that's true, then 1 also has to exit. And if this number is different than 1, say if here I have 1 and here I have exiting 0.9, that means that the density inside or the porosity must be changing, one of those. So those two compensate in order to write this diffusivity equation. All right. So I think, you know, we could do all the math that is required to do this, but probably I'll give it to you as a homework if you want to do it. But at the end of the day, the only thing we have to do is just to bring this term from what we had over there. Here we assume Darcy, so the flow rates are going to be expressed in terms of a permeability times a gradient of pressure. That's when pressure is going to come into the picture. We're also going to assume a homogeneous solid, porous solid, and that means that I'm going to be able to take the variation or the K, I'm going to be able to take the permeability inside the parentheses outside the gradient. And when I put these equations together and I assume Darcy, what we get is the following equation. And notice that also here, you see that this one is going to depend on pressure too. So this is going to be a dP. We're going to get, our objective is to make all these equations as a function of pressure. So from here, we're going to get this dP and these other parameters. And here already we have variation of time. So this equation tells me that the variation of pressure with variation of time is going to be equal to permeability. And let me call permeability, we have too many Ks. So let me call permeability KH. M times Biot Modulus divided by viscosity of the fluid, that comes from Darcy equation, times the Laplacian of pressure minus alpha Biot Modulus variation of volumetric strain with time. Okay, so just to do the math, and you will be equation, and let me write what this is. This is the diffusivity equation coupled with poroelasticity, linear poroelasticity. So those of you that have taken a course in, for example, reservoir simulation, you worked on solving this part of the equation. Variation of pressure as a function of variation of time. You have a question, Rodrigo?
Yeah, this Laplacian you said is just it's like a divergent, but for the second derivative?
Yes. Okay. This is the second derivative with respect to x2 times plus the second derivative with respect to y2 times plus the second derivative with respect to z2 times. That's the Laplacian. So notice that here Darcy, let's complete this. I'm going to help you a little bit. Q is equal to negative K divided by mu, this is KH, and times the gradient of pressure. This gradient of pressure is going to be a vector. So that's why this is a vector, this is a vector. And then when you apply this term, a dot product, to that vector, then you're going to get this summation of those terms. So as I was telling you, this part, without this, it's just a diffusivity equation. Usually, if you don't consider the poroelasticity part, this term M, which is the Biot Modulus in our equations, is just going to be the inverse of the compressibility, the total compressibility, which depends on the compressibility of the fluid and also depends on the rock compressibility. So it's a very similar term. But now we're adding this other component. And this other component, for example, tells you that you could cause variations of pressure as a function of time even without this type of variation. You could cause it by deforming the porous solid. Deforming of the porous solid is going to result in changes of pressure, or the same changes of pressure are going to cause deformations of the porous solid. And if you put everything together, then you can now solve the coupled system of poroelasticity with fluid flow. So this is just basically the part of solving the fluid flow part. All right, so we have now an equation as a function of time. And basically, with this equation, we can solve for transients. We're not going to solve this equation, so don't worry. But I want you to understand what this equation means. And it's just a diffusivity equation with a poroelastic part, and it accounts for variations of the bulk strain of the solid, of the porous solid, and how that can induce changes of pore pressure. And that's going to depend on the parameter M, but also on the fluid part, on the permeability of the solid, of the porous solid, and the viscosity of the porous solid. So let's just make this equation a little bit simpler for now in order to understand in terms of time what is the effect of those parameters, especially the ones that combine the fluid. So if I want to simplify this for just the diffusivity part, I could disregard the part of the variation of volumetric strain and say that this is just equal to the first part, in which this, what does this equation look like? Well, I think I told you in it. It's a diffusivity equation. So this is just a diffusion equation. Variation of pressure as a function of time with a second derivative with respect to space. So this is a diffusion equation. And if this is a diffusion equation, that means that this thing over here, we can think it as a diffusion parameter. It's pore pressure diffusion parameter. And a diffusion parameter will tell you how fast pore pressure diffuses given a rapid change. And this kind of makes sense because take a look at this equation. It tells you that, let's go for the easy ones. The bigger the permeability, the higher the diffusivity of that porous solid. That means that if you apply a load and you deform a solid, it's going to drain very quickly because it has a high permeability. If the solid has a very small viscosity, also is going to drain faster. A porous solid filled with a gas is going to drain a lot faster than a porous solid drill loaded with, filled with, say, an oil, a viscous oil, and subjected to the similar conditions, just because of the viscosity part. It takes more time to flow that viscous fluid throughout it. And the last one is the compressibility of the system, which in this case, it's not really compressibility, but it's in stiffness. The bigger the stiffness of that system, the higher the diffusivity of the medium is going to be. And we can simplify this further and say that assume for a typical load, which is, imagine that as a function of time, we apply a strain which is, starts with 0, but then changes suddenly to some value. If this is the case, because we're applying a strain, your pressure is going to change. So let's say the pressure was some value different than 0. Once you apply a load, the pressure may increase, but then it will reach to an asymptotic trend. How long time it takes to go into this asymptotic trend, you can solve it in simplifying form by what is called the characteristic time TCH, in which TCH is going to be proportional to the drainage length, which is, I'm going to explain what that is in a bit, but it's just L is the drainage length squared divided the diffusivity constant. And this diffusivity constant, I should clarify that its units are meters squared per second. So, all right, let me complete the picture of this experiment. This, what I mean is, let's imagine that I have a porous solid into an impermeable container. When I apply a load and I deform it, L is the drainage length, how much a fluid has to go in order to reach the condition in which pressure is going to be equal to 0. So, for example, if you push this from the top and you have a draining boundary, that means that the fluid can go through. All the fluid that is here at the bottom, or some of it, not all of it, will have to go all this distance in order to get to this free surface. If I had a case, for example, in which I have impermeable boundaries on the sides, and I apply stress from top and bottom, but I also let the fluid drain from the top and bottom, now the drainage distance is half of that. So in this case, L is going to be equal to that. If you know the length and if you know the diffusivity parameter, you can compute this characteristic time. And that, again, this characteristic time is going to tell you how long it takes for pore pressure to dissipate in a system. Not fully dissipate, because it is an asymptotic trend. But for this solution, this is more or less 2/3 of the change of pressure will correspond to that characteristic time. And for your project in poroelasticity, there was one question that was causing problems to many of you. This is actually what you have to do. You have to compare what is the characteristic time of the system, knowing all your other parameters, with the time in which it was loaded. So you will see that in the experiment in which I did that poroelastic determination of the Biot coefficient, you also have a characteristic time, which is the time it takes for the load to reach a certain value. So, for example, this is a different thing. If the mean stress or the confining pressure was increased at a given rate in this amount of time, this is the time I want you to compare. The experimental time with the characteristic time. If the characteristic time it's a lot smaller than the experimental time, that would mean that the process is, let me write that down. If the characteristic time is smaller than the delta t of the experiment, that would mean that, should that be drained or undrained? If the time is very small, that means that it drains very quickly. It drains very quickly, and that's smaller than the time in which you apply that law. That means that it's going to be a drain process. If the characteristic time is larger than the time of the experiment, that would mean this is undrained. And particularly in the experiment that you have to answer this question about, this is what was happening. You had a sample. The sample was in between these end caps. The end caps have holes that allow the pore pressure to dissipate. And as loading is applied, so this is the membrane, as loading is applied in all directions, your drainage length, because both of the pores were open, is going to be this, L. So half of the length of the sample. And I think the length is in there, right? But the length, if it's not there, is 2 inches, the total length of the specimen. It's very important that you notice from this equation that this characteristic time depends on 2 things. It depends on the drainage length and depends on the diffusivity parameter. Can anyone mention any undrained problem at geological scale? Because this is in the laboratory, but also happens in the field.
High pressure sandstones, reservoirs.
Okay, and why are they high pressures?
Because they are compacted so then the pore pressure doesn't have time enough to go on.
And what is compacting them? I'm following your example. I'm just trying to get the words out of you. You're right.
Other sediments.
Other sediments, right? So this is an example in the laboratory. But this same thing that I'm doing over here, it actually happens in nature. When you have a sedimentary basin, let's assume that we go offshore, and you have a bunch of sediments which are thrown into a basin, and layers of sediments start to pile up on top of each other. You may have at some locations places in which the rate of sedimentation, this point means rate, the rate of sedimentation may be larger than the rate of pore pressure diffusion. And when that happens, because probably here you're adding lots of sediments, they pile on top of each other, some of those sediments may have a low, if you're just piling up sands, you're not going to have any buildup of pore pressure. But if you're piling up silts with clays, and those are sediments with low permeability, the result of that is that in some of these layers, in some of these sediments, the pore pressure may be still locked in. I mean, it may be diffusing with time. So when that happens, as a function of depth, you may expect a hydrostatic pore pressure, but actually if you have, let's assume these are clean sands, so there is nothing, let me continue a little bit more my art over here. So this is sea floor, okay, and this is the sea level. It's a boat over there. You normally would expect hydrostatic pore pressure, but if you have this phenomenon in these layers, and if your permeability is low enough, you're going to have a deviation of the pore pressure, and the actual pore pressure, it may be hydrostatic up to a point, but once you start in the region in which pore pressure couldn't dissipate with time, pore pressure is going to deviate from hydrostatic pore pressure, and it's going to be some value which is higher than hydrostatic pore pressure. And this is what is called overpressure. And let me complete this. So this is the sea floor. And this overpressure is quantified by this parameter lambda p, which is just the ratio of pore pressure divided vertical stress. What is the maximum value of lambda p? 1, right? Can pore pressure be higher than vertical stress? No, you say no, Rodrigo, why?
Because if it's higher, it's probably going to fracture, right? Or
Yes. So first of all, we didn't talk about horizontal stresses yet. And first of all, the pore pressure has to be lower than the horizontal stress, because otherwise we would fracture it. And if the minimum stress is the vertical stress, it cannot be higher than the vertical stress, because we'll also fracture it. It could be higher, but just in short times. Over long times, that's not possible, because otherwise you will have like hydraulic fracture propagating forever, and that's not possible. So while the hydraulic fracturing propagates, it could be higher, but over long times, that's not going to be the case. But this is exactly what is happening over here. It's a similar problem, and it depends on this coupling between solid deformation, fluid deformation, and pore pressure. How changes in porosity can result in increases of pore pressure. And just to complete this phenomenon is called also disequilibrium compaction. So if you want to solve this as a function of time, because remember this one is you see right now, but if you were to let this one over millions of times dissipate, it will go to the hydrostatic trend. Okay. Let me think if there's something I'm forgetting. So just to give you an idea, I have some numbers here that probably will help illustrate this problem. We're going to come back to this problem of overpressure later on, in about 2 weeks from now, or 3 weeks. And I'm going to give you a real case that you're going to have to explain these anomalies in overpressure by measuring porosity. Okay, so let me see. Show it here. Okay, this is the same thing we have been discussing. Okay, this example. So, if you were to have a 100-meter thick sediment with same compressibility, or same stiffness in this case, and different permeability, a sand, typical sand, 100 millidarcy, or a mud rock with 100 nanodarcy, using the equation that we saw before, it would take about 1 day for that pressure to dissipate in the sand. It would take 3,000 years for that mud rock to dissipate the same amount of pressure. So permeability here, it plays a very important role, because this one over here, it varies in 6 orders of magnitude, so 1,000,000 times. And this is the difference also you can see over here. So if you have fast sedimentation rates, then it's very likely that you may have overpressure just because the water or any fluid in the sediments didn't have the time to escape with time. All right. Anyone could mention another example of undrained loading? So we have seen this example. Let's see, I have 2 more in here. Anyone has any suggestion? All right, let me tell you my ones. When you have a hydraulic fracture, especially hydraulic fracture in a low permeability rock, what you do is you open a space in the subsurface relatively quickly. In less than 1 hour, you open this fracture. As you open this fracture, in the face of the fracture, you increase what the stresses are near the fracture. As you increase the stresses near the fracture, what you cause is there are changes of shear stresses, change of normal stresses, but in general, what you will have is a change of volumetric strain, which is a contraction. If you have a contraction and you have a very low permeability, this rock is filled, let's say, with oil. What would you expect to happen to pressure? The pressure will tend to increase. So if this is undrained, that would mean that the pressure is going to increase. How much it increases? Again, it will depend on the properties of the rock, but especially on, in this case, the compressibility of the fluid inside. If you're doing this in a gas reservoir, the gas is going to have a high compressibility. Probably the increase in pore pressure is going to be small. But if you do this in an oil reservoir, that compressibility is going to be a lot smaller, and the change of pressure is going to be a lot higher. So by deforming the material next to a fracture, you can be inducing increases of pore pressure. And if you increase pore pressure, what's going to happen to effective stresses. Effective stresses are going to decrease. And if effective stresses decrease, we're going to see later on that that's going to get you closer to failure, and in case of some of these sediments or rocks, to shear failure or reactivation of natural fractures by increases of pore pressure.
You want another example
Yes.
of how you can develop overpressure?
Yes.
Can it happen on this or at the rate that like oxygenic cement would grow and essentially reduce pore space and increase pore pressure?
It could. I think it could. And I don't know if in some of those cases, in those inclusions, the pore pressure could go so high also that you may fracture some of those inclusions. I'm not sure. Or, for example, if you add the temperature too, if you increase temperature and then the fluids start to expand, also you can have overpressure. Okay, I had one more thing to say about this. So in the face of the fracture, we'll have compression, and that could lead to increase of pore pressure. What do you think is going to happen at the tip of the fracture?
Isn't it intention?
It's in tension. And if it is in tension, that means that the volumetric strain is going to get larger. If the volumetric strain gets larger, that means that the pore pressure is going to decrease. And that means that, in theory, effective stresses would go up. But it also means that sometimes you could lower the pressure at the tip of the fracture just because you are in an undrained process, you are causing a dilation of the porous solid. Some people have done simulations about hydraulic fracturing, and they predict negative pressures at the fracture tip. That's something that doesn't really make a lot of sense. But I think the problem is that they start with pressure equal to 0 in the medium, and that's why when they start with pressure equal to 0 as a simplification, the porous medium, and a positive pressure inside the fracture, then they get negative pressure here. But that doesn't make any sense, at least for absolute pressures. But I would expect in these cases that pore pressure may decrease at the tip of a fracture in an undrained process, because you are basically creating more porosity, and as you create more porosity, you need more fluid, and if this is undrained, that means that pressure has to go down. Okay, and another example of an undrained process caused by loading, it's also something which is called now as poroelastic interference. And what that means is that you could, let's say that you make a fracture somewhere over here in a vertical wellbore. Let's make it simple. If you have a monitoring well somewhere over here with pressure sensors, and again, if we're assuming that this is a very low permeability rock, even without having fluid that moves from here to here, just because of the effect of compressing the rock, you may have a change of pressure measured in these sensors. just because you are deforming the solid. And you could also think this a little bit differently, saying like, let me see if I can make this. So this is side view. If you have a top view, and now you have, okay, this is a vertical well. From a top view, if you have a horizontal wellbore, and here you have another horizontal well, but just for monitoring, and you have sensors in this. If you have a fracture that goes through close to those sensors, you could also measure a change of pore pressure because of the deformation it causes around the fracture. You wouldn't expect major changes of pore pressure unless there is some permeability channel that connects. But even if in the absence of changes of pore pressure because of fluid flow, you may sense some of these changes of strain because the rock is deforming and it's compressing the fluid inside the rock. So this is meant to be a hydraulic fracture. And another application of this, very similar to this one, is that, let me complete this. Today, Dr. Lake showed me something very interesting. It's a sock, which is like horizontal wellbore. So it starts like vertical, like a vertical wellbore, and then on the heel is like curves and goes to the toe, like a horizontal well with some small fractures. I'm going to try to get it. I'll show you. So in this case, I'm assuming this is the heel and this is the toe of the fracture. And this one is a hydraulic fracture. Okay, and the other example could be similar to this, but now let's say that you have a cap rock, and here you're injecting a fluid without any fracturing. If you have a monitoring well here with pressure transducers, along the well, even outside the reservoir, above the cap rock, you could sense the effect of the loading, because as you inject, this rock is going to expand, and as it expands, the deformation is going to travel further than what the actual fluid does, and you could also sense that in a formation which is above the cap rock. So in all of these cases, you measure a change of pore pressure because of deformation of the rock imparted by a hydraulic fracture or injection of fluid or change in pressure or any other thing that you could do in order to deform the rock. All right, so we just have a few more things to do about poroelasticity, and we're done, okay? So I think it's going to take probably, try to be quick, but it might be more or less 30 minutes. Or a little bit less. All right, so, and with this we finish undrained loading. First of all, it's very useful, for example, in this case of poroelastic monitoring, to get to know what will be the change of pore pressure due to a change in strain. So you have a rock, you strain it, let's say 1%, you compress it 1%, you want to know what is the pressure that's going to result from that compression under undrained conditions. So this is pore pressure change due to volumetric strain, and this is for undrained loading. But this is exactly what we were talking about before. You compress a rock, you do not let the fluids escape, and we want to know what that pressure is going to be. And in order to do that, simply what you have to do is to use this equation, diffusivity equation. So I'm going to assume here that this one is going to be equal to 0, and I'm assuming that there is no variation in time. So dP divided by dE is just going to be equal to alpha m, and that's it. So if I write what m is, it's going to be this value, and what this tells me is that, for example, this is the same also for the case of, we were saying, undrained loading next to a hydraulic fracture. The change of pore pressure is going, notice that this is the inverse, is going to be proportional to the bulk modulus of the fluid and the bulk modulus of the solid times the Biot coefficient. But if you have a very small bulk modulus or the very large fluid compressibility, this is going to be a huge number, and the inverse of a huge number is going to be something very small. So the change of pressure is going to be very small. So with these two, then coefficients plus the Biot coefficient and porosity, you can tell what is going to be the change of pressure due to a change of volumetric strain. And just let me complete this equation. This means undrained, and the cartoon for this would be a rock that you compress it, and as a result, pore pressure increases. Because you're compressing the pores, you're compressing the fluid, so pore pressure increases. All right. Second one. You may want to know how much stress you need in order to cause a given compression without letting the fluid escape again. And that's going to be a ratio of stress over strain. Do you remember what this is? This is the variation of mean stress divided the variation of volumetric strain, and let's say this is drained. So you let the fluid escape. What is that equal to? Basically, mean stress divided volumetric strain. The coefficient of proportionality is going to be, it's going to be a modulus, right? Which modulus? The bulk modulus K, or the K that we have called it bulk modulus, but before we can also call it drained, or sometimes we can also call it dry, because if we have a gas at atmospheric pressure, its compressibility is huge compared to the modulus of the rock, so it's just going to be that value. All right, so now we want to get the same thing. The ratio of the mean stress divided the ratio of volumetric strain, but under undrained conditions. And that, I'm going to call it Ku, which means undrained modulus. And in order to find out what is undrained modulus, we need to use the equations that we have derived before. So we know that mean stress depends on volumetric strain and on pressure, and therefore the variation of mean stress with variation of volumetric strain is just K minus alpha, the variation of pressure with variation of volumetric strain. But if you take a look at the equation that we have over here, it already tells me what that is under undrained conditions. So under undrained conditions, this is going to be equal to K minus alpha, and what I have over there, alpha m, and this is just equal to K plus alpha squared m. So which one is larger, Ku or K? Undrained modulus or drain modulus? The undrained modulus, right? Because this is plus, and m, we know that's a positive number, and the stiffer the solid and the stiffer the fluid inside the solid, the smaller the porosity, the smaller the Biot coefficient, the bigger this one is going to be. And here, now we're taking into account that we can compress a porous solid and also what is inside, and that equivalent bulk modulus is going to be this one. For many experiments, especially in shales, people measure Young modulus, measure bulk modulus, but the times that you need for the fluid to get out of these shales, it's very long. It can be sometimes months, and sometimes you cannot run a test in months. You run it in one day, in a few days at most. And in many of those cases, I think what people really measure is the undrained modulus, not the actual modulus. And you have to be careful about that, because these are not the same thing. Sometimes if the rock is too tight, you might be compressing the fluid inside without knowing that. All right. We are good over here, undrained bulk modulus. And it's going to take a little bit less than what I thought. The third type of parameter which is interesting to us in undrained loading is something which is called the Skempton's parameter. And the Skempton parameter tells you what is the variation of pore pressure due to a variation of mean stress. Again, I always forget to put this undrained condition here. For an undrained condition, this is called Skempton parameter, and it's called B. And again, you can work through the equations of poroelasticity and figure out what this Skempton parameter is. And if I follow what over here, just for the inverse of that, it's going to be K dE dP minus alpha, and I think I have this one from my previous equation, and it is just from the first one, alpha m, and finally Skempton parameter, and you can write it as this. You may ask, what is the Skempton parameter useful for? And the Skempton parameter is going to be, let me see if this is correct. Yes. The Skempton parameter is useful especially for you guys that work in geophysics and that measure wave velocities in the laboratory, whenever you have a rock and a porous rock, and you are measuring a P wave velocity, you want to make sure that your rock is fully saturated with the fluid, especially if you want to try to measure the P wave velocity with saturated conditions like in situ. And the issue there is that if the rock is not fully saturated, your P wave velocity is going to be a lot lower than it should actually be. And in order to check for that saturation, you want to measure this Biot Skempton, this Skempton parameter, and basically you do that by increasing the confining pressure and measuring under closed conditions on a pressure transducer what is the change in pore pressure. And only once your B tends to a value close to 1 or at least to an asymptotic value is when your rock is fully filled with fluid and, for example, liquid. Otherwise, it is not. And if it is not saturated with the liquid, then your P wave velocity is going to be, again, a lot lower than it should be with saturated conditions. Let me just finish that. So, for example, if you have, let's imagine just water saturation and this P wave velocity for 100% saturation. It might be some value over here. For 0% saturation, it might be some value over there. And this curve is something like this. It doesn't really pick up until you get very close to saturation of almost incompressible fluid. So anywhere you are in between, before 100% saturation, your P wave velocity is going to be very low, and your geophysical measurements are not going to be good. All right, I think with that, we have finished this part of poroelasticity and the undrained part. And this is going to be everything included for the exam. And well, Jack is not here, so probably we don't have this review session, right? I don't know, what do you guys want? Do you want to have a review session? Or yes? Well, all right, well then just prepare some questions, okay? I think it's going to be better that you prepare a question other than me just going over the material again. Probably we can go over the homework solutions as well, and I will need some of you to upload your solution as soon as possible, so I can upload also the solved solution, okay? And then we'll talk about the exam then on Wednesday. Oh, because we have the exam, right? We can do that, but I strongly recommend that you solve it, okay? At least the first part. Second part that requires the use of CMG, you may do that later on. But it's also very useful, that part. So try to do everything, but you don't have to upload it by Friday, okay? Did you guys try to go to a computer lab and use CMG? You did? It works? No problem? All the files that you have are fine? Yeah. All right. So if you need help again, you can talk to Jojin. He's back. He wasn't feeling well last week, but now he's back, and he should be able to help you. All right? Okay, well, I'll see you on Wednesday then. Thank you.